Hello, everyone, and welcome to today's webinar brought to you by Avnan. We're excited to talk to you today about how to build a better HVAC landscape for 2026 with intelligent controls and advanced diagnostics. My name is Georgia Roberts, the Marketing Manager at Avnan, and I'll be your host for today's webinar. The webinar will run about an hour, and we hope to have some time at the end for some Q&A. Please submit your questions in the Q&A section at any time. We'll try to answer as many as possible. Everyone will also receive the webinar recording after today's session. Also, feel free to subscribe to our YouTube channel and LinkedIn for notifications on new webinars and videos from Avnan. You can find the links in the resources section. For those not familiar with Avnan, we partner with OEMs to provide complete electronic product solutions, from design and manufacturing to strategic sourcing and supply chain management. With a flexible global manufacturing footprint across China, Taiwan, Hong Kong, Vietnam, and India, we deliver end-to-end solutions to industries such as HVAC, appliances, building automation, and many more. You can learn more about us by visiting our website at avnan.com. We also have some materials and links in the resources section. All right, let's get started. I'd like to introduce you to our speaker today, Adam Lawrence, Senior Firmware Developer at Avnan.
Hello, everyone. I appreciate you joining us today. As Georgia mentioned, I'm a Senior Firmware Developer here at Avnan with over 25 years in electronic product development and production. My expertise is in embedded development and test automation. Before we get started, let me give you a quick overview of what we'll be covering today. We'll start with how a universal controller platform can simplify your product architecture, reduce design complexity, and help standardize diagnostics across your product line. From there, we'll look at how to build a strong diagnostics foundation. Things such as unified fault codes, onboard data logging, and how consistent messaging can make life easier for techs and service teams. We will then shift into how systems handle issues, safe shutdown logic, fault response ladders, and how those align with safety certification requirements. We'll also touch on traceability and firmware best practices, because as systems get smarter, it's critical to keep software updates organized and auditable. We will also look at the major regulatory trends shaping the future, like energy efficiency rules, refrigerant changes, indoor air quality codes, and cybersecurity laws. After that, we'll dig into what modern control software should look like, built-in self-tests, standardized protocols, and clearer service messages. We will then bring it all together on how to use controller data for real-time optimization, like fine-tuning capacity and airflow dynamically, and how predictive analytics can drive smarter maintenance. Finally, we'll wrap up with how all this applies back at the factory, using embedded diagnostics to speed up end-of-line testing and feed field data back into future product designs. And of course, we'll leave some time at the end for your questions. Let's dive in. Let's first talk about the foundation of intelligent HVAC systems, designing a controller architecture that is unified, reliable, and rich with diagnostics. Many of you are HVAC system architects or product managers, so you understand the challenges. Imagine you're an OEM with a lineup of heat pumps, air handlers, and fan coil units. Traditionally, you might design a separate control board for each model, each with its own traits. But the industry is moving away from that siloed approach. Instead, we see a push for one universal controller platform that can be adapted across all those products. In practice, many manufacturers are already moving in this direction, a common control architecture that can scale from a small residential unit up to a large commercial system with just configuration or minor hardware differences. Why is this happening? It's driven by the need to streamline development, ensure consistency, and speed up time to market. A scalable, universal controller means you develop and validate one core platform and reuse it, which saves engineering effort and reduces bugs. It also means a consistent user experience and performance across your product line, From a manufacturer's perspective, this strategy cuts down design costs and inventory complexity. From a technician's perspective, it means familiar interfaces and diagnostics, no matter which unit they're servicing. And for the end customer or building operator, it translates to more reliable equipment and easier support. It's a win-win, driven by market demand for more standardized, connected HVAC systems. From a technical standpoint, a scalable controller architecture typically includes a powerful microcontroller, a flexible I/O matrix that can be configured per product variant, and multiple communication interfaces. We now embed edge computing capability, so the controller can process data in real time, locally, without always needing cloud connectivity. This is important for running complex control loops and diagnostics on the fly. Modular design is key too. For example, you might have plug-and-play modules for different compressor types or an expansion slot for extra sensors or future add-ons. Using standardized communication protocols such as BACnet ensures any unit can talk seamlessly to building management systems or IoT cloud platforms. A common platform adhering to these standards position your HVAC products to integrate into the broader building automation ecosystem right out of the box. In parallel, residential HVAC controllers are now incorporating edge capabilities to integrate seamlessly with smart home ecosystems. For example, many modern units support voice assistant platforms like Amazon Alexa and adopt emerging smart home standards such as Matter, enabling homeowners to manage their climate with simple voice commands or through unified home apps. Essentially, the onboard edge intelligence ensures these features work in real time, even if cloud connectivity drops, so the system can still run schedules or respond to sensors locally. Embracing these consumer-friendly protocols means a residential HVAC unit can plug and play into a homeowner's smart home network out of the box, much like how open standards enable commercial systems to slot into building automation. Another key part of the architecture is onboard memory with integrated data logging. By capturing key sensor readings and events, the controller builds a structured data trail that supports your diagnostic strategy. This built-in logging allows technicians and engineers to instantly see faults and the conditions that caused them, without external data loggers or recreating conditions, allowing faster troubleshooting, less downtime, and higher reliability. Beyond simply recording data, the log's standardized structure makes it easy to interpret and align seamlessly with the diagnostics framework built into every unit, shifting from basic control to intelligent monitoring and analysis. The next key step in building this framework is creating a structured fault taxonomy, a standardized system of fault codes and categories consistently applied across your entire product line. If every product or every team uses different names for the same fault, it creates confusion. One model's software might log a damper issue as discharge air damper hunting, while another calls the same behavior damper cycling instability. This may seem trivial, but inconsistent fault naming leads to this confusion and makes it harder to analyze issues across a fleet of equipment. By developing a unified fault code library, service teams can interpret fault codes quickly without cross-referencing multiple manuals. A technician who's used to seeing a fault code on one system will immediately recognize it on another. The knowledge transfers instantly across the product line. This will ultimately accelerate troubleshooting and reduce training needs. For the manufacturer, it means your support hotline or service department isn't getting bogged down deciphering codes on different models. It's all standardized, which ultimately improves customer satisfaction. Beyond naming, a disciplined fault strategy includes categorizing faults by severity and subsystem. For instance, you define which faults are warnings, such as a dirty filter, and which are critical, such as a compressor overheating. By doing so uniformly, you can also implement consistent responses. One area where that consistency pays off is how the system reacts when faults occur. Not all faults are equal. Some allow the system to keep running in a limited way, while others require an immediate shutdown to protect equipment or safety. To manage those varying fault levels consistently, we use the concept of a safe shutdown ladder, which is basically a hierarchical sequence of actions the controller will take as a fault condition escalates. For example, imagine the condenser coil temperature is climbing too high. At the first sign of overheat, the controller might take a mild corrective action, like ramping down the compressor or increasing the fan speed. That's rung 1 of the ladder, trying to self-correct. If the temperature keeps rising, the fault condition worsens, rung 2 might open an emergency damper or cut off the compressor for short intervals. And if it becomes a severe overheat, indicating a potentially dangerous condition, rung 3 is an orderly shutdown of the system. This progressive response protects the hardware from catastrophic failure and can prevent hazards. No one wants a compressor burning out or a high-pressure blow-off. Importantly, each step should also log what's happening and alert the user, so it's clear what action was taken and why. Safe shutdown sequences handle faults gracefully. This approach aligns with industry safety standards and expectations. In fact, many safety standards insist that for certain critical failures, controllers must initiate an automatic safe shutdown within a specified time. And new safety regulations are raising the bar in HVAC as well. For instance, UL 60335-240 responds to the introduction of mildly flammable refrigerants by requiring robust measures to mitigate fire risks. This means controllers need to be smart enough to detect issues like a refrigerant leak or ignition risk, and then take appropriate safe actions. So, having these ladders baked into your firmware isn't just good practice, it's a compliance requirement. Now, let's talk about something a bit behind the scenes, but very important: firmware traceability. As you all know, HVAC controllers today are essentially embedded computers. Managing the firmware lifecycle, versions, updates, bug fixes, has become a major part of delivering a reliable product. Firmware traceability includes a clearly identifiable version number and a build date that can be accessed by technicians in the field directly from the controller. This allows for immediate identification of the software running on a specific unit. A comprehensive change log is essential and maintained in the development system. This log meticulously links each firmware version to its specific modifications, including new features, resolved bugs, and any identified known issues. This provides a historical record of all changes. The advent of IoT connectivity mandates the implementation of these practices. Modern HVAC systems can now automatically transmit firmware version information to cloud-based platforms, enabling remote monitoring and management of firmware across a fleet of units. This allows for centralized tracking of which units are running which firmware versions. The real value of traceability shows up when there is an unusual intermittent fault in the field. Suppose we start getting reports that a certain model heat pump is sporadically throwing a false pressure alarm. If we know these units are running firmware version 3.1 and our logs show we updated the pressure sensor algorithm in version 3.2, that's a huge clue. We can quickly zero in. Maybe version 3.1 had a bug that was fixed, so the solution is simply to update those units to current firmware. From the manufacturer's perspective, this is about protecting quality and reacting fast to issues. It can be the difference between a minor field bulletin or a full-blown recall. Before we look at specific regulations, it's worth stepping back and recognizing that the HVAC industry is taking cues from safety-critical sectors like automotive and medical devices. For instance, in medical and automotive, traceability and self-diagnostics aren't just best practices, they are requirements. Standards like IEC 62304 for medical software and ISO 26262 for automotive electronics enforce strict controls around fault detection, documentation, and safe behavior. The newer ISO 24089 even covers how updates must be engineered and delivered securely. While HVAC isn't as tightly regulated yet, we're seeing a shift towards this level of discipline, especially as systems become more software-driven. For example, today's microcontrollers increasingly perform startup self-checks to verify memory, sensor inputs, and safety paths before allowing operation. That's traceability and diagnostics being baked right into the firmware, just like in a car or a medical device. Now let's talk about the key regulatory changes that are driving real change in HVAC control systems, what's coming, and what it means for all of us. First up, the Department of Energy's new SEER2 and IEER standards. These kicked in January 2023 and increased the bar for energy efficiency. Units must now perform 7 to 15% better under more realistic test conditions. To hit those targets, manufacturers have to move towards variable speed compressors, precise fan modulation, and smarter control loops. For us in controls, that means our systems need more diagnostic depth and tighter feedback control. Secondly, refrigeration requirements. The U.S. AIM Act and California Title 24 are phasing out high GWP refrigerants. New systems must use low GWP A2L refrigerants, which are mildly flammable. That triggers safety requirements under UL 60335-240, including built-in leak detection, ventilation triggering, and fail-safe shutdown modes. Control boards must now include sensors, logic, and fault recovery built to handle these new refrigerant realities. Thirdly, indoor air quality codes. The ASHRAE 241 standard and updates to Title 24 require better ventilation control. Think demand-controlled ventilation based on CO2 sensors, occupancy, and IAQ feedback. Controllers must now modulate dampers and fan speeds dynamically, balancing air quality and energy use. These standards are already reshaping residential and commercial HVAC design. And finally, one thing that's possibly flying under the radar for many OEMs, the European Union Cyber Resilience Act. This regulation, which will come fully into play by late 2027, will require every connected controller sold in Europe to be secure by design, supporting encrypted communication, authenticated firmware updates, and in some cases, third-party certification. Even if you don't sell in Europe today, this is going to shape expectations globally. The writing's on the wall. If your controller connects to the internet or building network, it's going to need stronger cybersecurity controls, secure firmware, and traceability mechanisms. So, what does this all mean? These emerging standards on energy, refrigerants, air quality, and security are pushing HVAC controls to evolve. Over the next few years, systems will need to support more sensing, smarter algorithms, real-time fault management, and secure, updatable software. In short, smarter, safer, more connected controls won't just be a competitive edge. They'll be required to meet regulations and customer expectations. And the best part? Much of the groundwork, like diagnostics, traceability, and modular platforms, is already within reach if you're designing for it now. Now that we looked at how evolving standards are pushing the industry towards smarter, safer control systems, let's talk about what that means in practice, especially at the firmware level. One of the most important things you can build into your control software today is traceability, clear versioning, change logs, and audit trails that show what firmware is running, when it was updated, and what it changed. This isn't just helpful for troubleshooting, it's increasingly necessary for compliance and cybersecurity readiness. Alongside that, we're also seeing a strong move toward built-in self-diagnostic routines. These routines perform hardware checks, sensor validation, and internal consistency checks during operation or startup. Together, traceability and self-diagnostics form the backbone of a resilient, serviceable control platform. So, with those elements in place, let's shift our focus to the more frontline side of diagnostics, the part that technicians and users interact with directly, fault codes, service messages, and the on-screen data that drives field service decisions. Designing these service messages is part of the firmware development. It ties back to the unified fault taxonomy. Each fault code has an associated message or troubleshooting tip. Best practice is to work with your tech support and field engineer teams to craft those messages so they're as helpful as possible. Think of it as embedding a troubleshooting guide into the unit. In some cases, the controller might even take preemptive actions when a fault is imminent and pop up a warning like airflow low, check ducts or blower, before it triggers a high-pressure cutout. This kind of proactive diagnostic is aligned with the broader industry trend of predictive maintenance, of using analytics and rich diagnostics to reduce unplanned downtime by enabling proactive service. I want to quickly touch on some standards and best practices relevant to everything we've discussed so far with architecture and diagnostics. It's not just about doing these things in isolation. Aligning with industry standards can future-proof your designs and make integration smoother. We mentioned UL 60335-2-40 for appliances, which is prominent right now due to refrigerant changes. Also, UL 1998 for safety of software, and IEC 60730 for control systems are relevant. They encourage having self-diagnostics and fail-safes in your control software. Even if not strictly required for all HVAC equipment, adhering to these principles will ensure a higher level of robustness. We've also already talked a little bit about BACnet. Using BACnet's standard objects for sensors, alarms, and faults means that when your unit is connected to a building management system, it can broadcast its status in a way that the BMS natively understands. The data is clear and unambiguous. ASHRAE has a committee on fault detection and diagnostics. The industry is moving toward some level of standardization in how faults are named and categorized for analytics purposes. For example, ASHRAE's Guideline 36 for high-performance sequences of operation touches on standardized alarms for HVAC control sequences. Keeping an eye on these can help you align your fault taxonomy with what may become an industry norm. Best practice is that all those logs and diagnostic data we put in the controller should be easily accessible to technicians and engineers. That might mean a USB port for a laptop tool, a Bluetooth interface for a mobile app, or cloud connectivity. The key is, don't trap the valuable data on the board. Use it as part of your service strategy. To wrap up this section, a scalable controller architecture plus a robust diagnostics blueprint, fault taxonomy, safe shutdown, traceability, clear messaging together form a platform you can deploy across your product lines. This improves your internal efficiency, enhances the technician experience, and ultimately results in more reliable, smarter HVAC products for end users. It's very much in line with where the 2026 HVAC landscape is headed: more connectivity, more intelligence, and higher expectations for reliability and serviceability. Now that we have these intelligent controllers feeding us rich data, what can we do with that data beyond just troubleshooting? One game-changing application is using diagnostics and performance data to inform both system design and dynamic operation, essentially using feedback to right-size and fine-tune HVAC systems continuously. This is an area where we're shifting from one-time engineering decisions to ongoing data-driven adjustments. Today, diagnostics let us refine those decisions in real time and also loop the insights back into design improvements. Let's consider capacity first. We design a heat pump or AC with a certain BTU rating, but the actual demand can vary with weather, occupancy changes, building modifications, and so on. With embedded sensors and logging, the controller can measure how often and how hard the system is running to meet set point. If the compressor is at full output for extended periods and still not maintaining temperature on the hottest days, that's a clue that the unit is undersized for the load. Conversely, if it's short cycling frequently, it might be oversized. The value here is for both the customer and the manufacturer. The customer gets actionable info to upgrade or adjust their system before a failure occurs, preventing downtime. The manufacturer potentially gets a sales opportunity, or at least a satisfied customer who isn't upset about poor performance, because you gave them insight. On the design side, if you collect this kind of field data across many installations, it feeds into better sizing recommendations and product design. This ties into the trend of analytics and predictive maintenance we mentioned. It's not just predicting failures, but predicting needs. The industry is recognizing that continuous commissioning, that is to say, reevaluating system performance over time, can save a lot of energy and headaches. Right sizing isn't only about cooling and heating capacity. Airflow is critical to HVAC performance, efficiency, and indoor air quality. Now, with Diagnostics, we can actively adjust airflow based on real-time needs and conditions. For instance, if your controller detects that the temperature delta across the coil is smaller than expected, it can decide to adjust the blower speed to allow more heat exchange and better dehumidification. This kind of demand-controlled ventilation and airflow is increasingly expected. Standards like ASHRAE 62.1 encourage, and in some cases require, dynamic ventilation control to maintain air quality without wasting energy. Many modern systems are doing exactly this, modulating outside air dampers based on CO2 readings to hit the target indoor air quality. The benefit to the building owner is twofold: better occupant comfort and energy savings. You're not over-ventilating empty spaces, wasting energy, and you're not under-ventilating a packed conference room, avoiding drowsy occupants and high CO2 complaints. 2026 trends explicitly highlight upgrades such as CO2 sensors, better filtration, and UVC, all aimed at indoor air quality and health. A diagnostics-driven airflow control that can integrate those sensors is exactly what meets that demand. Modern HVAC controllers can read a variety of sensors: temperature, pressure, humidity, indoor air quality, and electrical measurements. All these data points feed into algorithms in the firmware. Some algorithms might be simple threshold-based logic. If the coil delta temperature is low and the compressor is at full speed for a long time, flag low performance. Others can be more complex, such as model-based or machine learning algorithms that learn the system's normal signatures and detect anomalies. Some advanced controllers implement performance maps or AI models to continuously compare expected versus actual performance. While full AI might be in the cloud domain, local controllers are quite capable now to do these sophisticated analytics. But even without AI, you can cover a lot with physics-based logic and statistical triggers. The key is using the data to actively adjust control parameters. For example, many variable speed systems use PID control loops. Those loops can have adaptive tuning. The controller can shorten or lengthen compressor cycles based on pass oscillations to eliminate overshoot. Or consider multi-stage equipment. A two-stage compressor unit can decide to stay in low stage longer if it sees that it's maintaining set point, thus saving energy and reducing wear. These decisions can be guided by algorithms that were developed using fleet data. Maybe your company analyzed hundreds of installations and found that for moderate days, running longer on low stage is more efficient than cycling high stage. You bake that insight into the firmware as a rule. By unifying continuous data logging with predictive algorithms, the controller forms a closed feedback loop between real-world performance and control logic. The onboard data continuously informs and fine-tunes these predictive and rule-based models, allowing them to adapt dynamically to changing conditions within your facility. This ongoing cycle bridges the gap between theoretical design and actual operation, ensuring the controller consistently optimizes performance, efficiency, and reliability based on live system feedback rather than fixed assumptions. From an outcomes perspective, all these data-driven control refinements yield significant benefits: improved comfort, efficiency, and equipment longevity. There's evidence that smart controls and IoT integration in HVAC can provide on the order of 10 to 15% energy savings and faster fault resolution through such optimization. And with sustainability goals and regulations ramping up, such as the US DOE's efficiency metrics SEER2 and HSPF2, these intelligent control strategies are key tools for manufacturer compliance and for customer energy savings. So, in summary of this section, diagnostic data is not just for alarms. It's a continuous feedback mechanism that can optimize system performance in real time and guide long-term decisions. It helps right-size equipment, dynamically tune airflow and capacity, comply with ventilation and efficiency standards, and make servicing more precise. The market is demanding these capabilities. Building owners want assurance that their systems will adapt to their needs and not waste energy. And technicians want tools that make their jobs more like using a diagnostic scanner on a car rather than pure trial and error. Fortunately, with the intelligent controllers we now have, we can deliver exactly that. Our diagnostics journey wouldn't be complete if we didn't take it all the way back to the factory floor. The final piece of the puzzle is leveraging these smart controllers during manufacturing and quality control to ensure each unit that goes out the door is rock solid. In other words, use the controller's own intelligence and I/O to streamline end-of-line testing and reduce the chances of defective units escaping into the field. At Avnan, we take end-of-line testing seriously. It's the final safeguard, ensuring every controller leaving the factory performs flawlessly in the field. Each board is engineered with design for test principles to enable maximum coverage in minimal time. Examples of this include using built-in access points and diagnostics to enable fast, thorough validation, using the controller's communication protocols, be it Modbus, RS-485, CAN, or Wi-Fi, to replicate actual operating conditions, built-in self-tests to verify sensor calibration, memory integrity, and I/O performance, meeting IEC 60730 Class B standards, simulation of edge case scenarios such as low voltage, safety trips, or sensor faults to confirm robust system response, digitally logging test data with timestamps and serial numbers for full traceability and ongoing quality improvement. This disciplined process minimizes escapes, strengthens reliability, and aligns with ISO 9001 best practices. The job isn't done when the unit ships. That's when we start learning how it really behaves. Smart controls make products living assets. They continue to tell us how to improve. One example might be noticing a lot of evaporator coil frost warnings in one model of heat pump, more than expected. By analyzing the conditions from the logs, you can discover that in a particular defrost cycle logic, there was a timing issue. It wasn't defrosting quite long enough under certain humidity conditions. So over multiple cycles, ice was slowly accumulating. You can then tweak the firmware defrost algorithm in the next update and also update the installation guidelines to emphasize proper airflow in those scenarios. Without the rich data from the controller, you might just get vague complaints of unit not heating well and not pinpoint the causes effectively. From the business perspective, this continuous improvement loop drives better products and can set you apart. Customers notice when each new generation of your product gets more reliable and intelligent. By leveraging the data, you're effectively engineering based on real-world evidence rather than lab tests or theoretical calculations. It's a very, very powerful approach and one that industries like automotive have been doing for years, using OBD data, warranty data, and so on. The HVAC industry is catching up fast, especially as equipment becomes more high-tech. So, tying up this section, using the controller's I/O and smarts in manufacturing testing ensures every unit is verified to perform and be safe before it leaves the plant, drastically reducing escapes of defects. It speeds up production and gives you a trove of data for quality control. And more importantly, it doesn't end there. Those same diagnostics continue to serve through the product's life. feeding information back to make the next products even better. It's a holistic approach from cradle to grave, powered by intelligent controls. As we wrap up today's discussion, I want to leave you with one thought. Everything we've explored, whether it's fault handling, safe shutdown logic, or standardized diagnostics, points to one clear direction. Intelligent control isn't just about efficiency anymore. It's about building systems that can understand, adapt, and protect themselves. That belief has been a driving force behind our work at Avnan. Before we move into Q&A, I'd like to take a quick moment to share how we're putting those ideas into practice through our own innovations. Our heat pump control and diagnostic platform is built around that same philosophy, helping manufacturers optimize performance through diagnostics that are truly customized to the equipment's behavior. And the same approach extends across our other technology platforms, from the universal controller to the fan coil controller, each designed to deliver flexible, diagnostics-driven performance that adapts to the unique needs of every system. We have included links in the resources section if you want to know more about our technology platforms. Okay, I'll now turn it back to Georgia for the Q&A section of this one.
Thank you, Adam. You gave us a ton of information today, so thank you. We do have some questions that have come in. The first question, legacy product line that uses different controllers for each model, just as a first step towards a unified controller architecture, everything.
Very good question. You can transition to a new unified platform very gradually. Obviously, you would identify a core controller that can replace several of the ones you already have in your product line. You would obviously want to dry run and test it on maybe a low runner or on a product that already has an update cycle coming. You need to think about your fault code taxonomy, make sure that you have everything defined for all of the models that you intend to run this controller on. Thinking of this in advance will definitely speed up implementing this on your other products as you move forward with the changeover. So, very good question.
Okay, the second question is, how do advanced diagnostics impact the training of HVAC technicians? Is there a risk that techs rely too much on what the controller says?
That's interesting. Like we talked about in the talk earlier, the diagnostic information that we're imagining is going to become very similar to the OBD2 codes that cars are spitting out. I would not dare say that auto mechanics today are less skilled than the ones from 50 years ago that had to rely just on their feeling. The systems themselves are much more complicated, and they need that insight coming from the controller to help steer them into a correct troubleshooting mindset. I think that these sort of troubleshooting codes that are coming out are actually helping to make the younger, less experienced technicians get up to speed faster. It's like there's a mentor in every controller, sort of helping guide them as they refine their craft. Yeah, very, very good insight.
I agree. Here, we collect a lot of data from units in the field. Any advice on data and actually using it effectively?
Oh, yes. Yes. Once you have the data, you definitely have to do something with it. So you do need to invest in some technology. You need to consolidate and you need to summarize this data. Usually you'll set up dashboards that can show you some specific metrics that are important to your company. From an engineering standpoint, you might be looking at metrics like average energy consumption. If you're looking at it from a quality perspective, you'd be looking at your fault rate per certain hours of operation. and you use that data to guide your decisions. Like, do you need to do an engineering update on a model? Are you actually meeting the energy savings targets that you set out for? Are you exceeding them? Then you can update your marketing material. But yeah, you just can't have the data sitting there doing nothing. You really have to have some people on it full time, crunching it, analyzing it, and seeing what insights you can get.
Okay, great. We have one last question. Can predictive algorithms be customized for different OEM applications?
Yeah, absolutely. The predictive part of the algorithm is really more a function of just the data collection exercise, the controller being able to measure everything it needs to measure, have a history of the measurements, and have enough processing power to create these prediction models. So the actual core application is not so important here. It's really the diagnostic and the data collection side of it that allows the predictive algorithms to work. So yes, in theory, you could have these on just about any controller you could imagine.
That's great. Thank you, Adam. It looks like we're at the end of the webinar. I want to thank everyone for attending today, and a big thank you to Adam for him sharing his expertise. We hope you enjoyed the webinar, and we'll be sending out the recording to everyone tomorrow. Thank you again, and have a great day.